Let's go back and see what's remaining. So the concept was clear, right? Let's see, there are some some special examples there, like for backstepping. So we have some backstepping continued. Okay. So this is an example. For example, eta dot equals to minus eta plus eta square z, and then or this is not a good variable, I don't know. Zeta dot equals to u. This example, for example. So what will be the approach? How would you approach this problem? Right? First, if v1 equals to half eta square, right? So what is v1 dot? Eta dot, which is minus eta square plus eta cube zeta. Okay? So now if I have to choose zeta to make v1 dot negative definite, what will be that?
Repeat the question. If you have to do what to make what negative?
Like if I have
I
to...
just didn't hear you. Can you repeat it?
So my question is, if I want to make this negative definite, what zeta should I choose? See, we are dealing with state by state, right? So we want to first make eta go to 0, thinking zeta is the input to the system, right? What should be zeta here such that...
-1
Huh?
-1
Maybe zeta equals to 0. That's a special example, right? So maybe zeta equals to 0, right? Can it... Let's see, at least try that zeta desired equals to 0. If that is 0, then that's just eta square, and then things are good, right? Let's see if it will work out. So, so basically, then v2...
u equals to 0, right?
Yeah. Zeta is, this is like phi of n kind of thing, right? That's we are choosing. So we can do is, so if, so basically in this case, zeta minus zeta desired, which is 0, equals to z, right? So basically z equals to zeta, in this case the error state. So this is eta dot minus eta plus eta square z, right? And z dot equals to u, basically not a problem. And then let's see, v2 can be, then we want z to go 0, so v1 plus half z squared. Then v2 dot equals to v1 dot, which is equals to minus eta square plus eta cube z plus z dot. So basically z into u. So that means minus eta square plus z eta cube plus u. So basically what u can we choose? U can be, cancel this out, that's a bad term. So minus eta cube, and to make it minus kz square. See, we always want things to be negative definite. So minus kz should give us v2 dot equals to minus eta square minus kz square. This k can be one, whatever you want to choose, right? So it's a gain kind of thing. So that's your control input. Okay, so that can happen. You can, but this is like in this case you could have started here, right? It's a simple half eta square plus half z square, no problem. Right? So it's the same. It's a simpler thing. Anyways, that's one example. Another example can be. Now let's combine things now. Okay, we have sliding mode, we have backstepping, and let's see if we can how we will use this, and then also show you some simulation maybe. So backstepping, and I have quadcopter and everything examples for later on, but we're getting started. I'm taking things slow. Undergrads keep saying me takes things slow.
They're so needy.
Actually, they are worried.
Yeah, that's who.
That's the whole university system. Like I want to say them, don't worry about it. I can give you any grade you want. Just work on it. Just come and tell me what grade you want. And I can say that actually. If they want to do it that way.
They need to learn it though. Like I can tell by the questions I ask. I don't want to hijack the class, but there's simple stuff I'll ask and they're not putting it together yet. It's just I don't know how to fix that part though. But anyway, they don't need A's.
Mm-hmm. x1 dot equals to theta 1 phi of x1 plus x2, and x2 dot equals to phi of x1 or theta 2 phi of x1 x2 plus u. So this is our awesome problem that we want to solve, right? Objective as usual, x1 goes to 0, x2 goes to 0. To make it asymptotically stable, you have to choose u, which makes it asymptotically stable. And now it's given to you that theta 1 is between a and theta 2 is b, less than b. You know this, what does this mean? You guys know that?
Yeah.
So basically I can write also like this, right? Theta 1 is greater than equal to minus a, greater than equal to minus or plus a. This is the same as saying this, right? So okay. And so parameters are not known to us directly, right? So theta 1, theta 2 are some parameters, and this problem we will also solve with adaptive later on. But right now let's assume that in adaptive we don't know anything about the parameter. That's it will be very useful. Here at least I know upper and lower bound of parameters. But in adaptive can be used even if you don't exactly know the parameter. Like for example your autopilot gains, right? Sometimes the gains that and I was asking a question in your EKF, right? How do you know these gains? So those are the places where you can use adaptive control, like you selected an autopilot whose gain are not known to you. Like for example, psi dot equals to kp into psi desired minus psi, right? A lot of controllers use this, but this kp, who knows?
Yes, yeah.
So if you are using that kind of problems, you can actually use adaptive control where you don't know kp, but still you can go. So we will get to that point, but for now, let's say we know upper and lower bound, and phi and psi functions, which are these, right? This and this are known to us.
So the auto tuning, it uses adaptive control.
A kind of not auto tuning, I would say. We will get there. It's a different kind of concept. You think that we are actually estimating parameter, but they are more than estimating the parameter. It's the rate, the adaptation rate, which is important. We'll get to that thing. So you never exactly estimate the parameter, but the rate at which it changes helps you cancel out things, and again it comes to negative definiteness and all that. Right? So let's start here. So what So now you see that like there is a need that adaptive will be, or the backstepping will be needed because u is here, right? At the u is here, right? Because u is here, you will have to use a sliding mode, right? No, sorry, backstepping.
Backstepping.
Because, and then because thetas are not known exactly, you will have to use sliding mode concepts there. So let's get started. So first, let's tackle this. Same, keep doing backstepping as you're doing, and wherever sliding mode concepts are needed, we will use those. Okay. So again, just let's say, hey, v1 equals to half x1 squared. That's what I want to solve. I want to. That's the good thing about control. Since we have using control, we don't have to use very complicated Lyapunov candidate functions because we have that choice that I can choose x2 to make any Lyapunov candidate function that is choose to make it negative definite. So that's a good thing. You get away with simple Lyapunov candidate functions squared are enough to this problem. That's so all the maths that you did in chapter 4 and all, it's good, but just to give you the feel of the problem. But I think most of the time here we can get away with. So what will be v1 dot? v1 dot will be so it will be theta 1. So I don't know if anything is given about phi x1, phi x2 or not, but for now let's assume that some properties should have been given, like phi x1 equals to 0 or not. But anyways, theta 1, maybe it's given in the book somewhere. I don't know. Just give me a minute. I don't think so. Anyways, if we'll get to the point if we need it. So theta, right? So it will be basically x1 into theta 1 phi of x1 plus x2, right? So that's what it is. So it will be this, right? So it will be x1 theta 1 phi of x1 plus x1 x2, right? Now what should be, so now we have to choose beta x2 to make this negative definite, right? So you see how the Lyapunov, the sliding mode is coming into picture. So the idea is we can say v1 dot is less than equal to your mode of x1 multiplied by mode of theta 1 and phi x1, right? Just take the norms and we can keep this as this because now I want to choose x2 such this whole thing goes negative definite, right? So what will I choose? So if you see, if I choose x2 to be x2 desired, we can call it x2 desired to be minus sine. So sine of x1 multiplied by x1 gives me absolute x1, right? So that's one, and then something greater than this, right? So it will be minus of theta 1. What is the upper bound on? So this theta 1 can be considered to be a, right? So this can go a because if you see here, it's a, upper bounded by a, right? So we can say, let's say, so you can say a phi of x1 plus some beta 0 into this. See, so let me rewrite it. x2 desired equals to minus a phi of x1 plus beta 0 into sine of x1. If that's the x2 desired, then you know that v1 dot will be less than equals to minus beta 0 of x1.
So 2 questions.
Mhm.
How can you assume, why do you put absolute values between this, from this step to this step?
Oh, so that's a good,
How does
that's a,
that not
the,
change the value of?
that's a great question, because see, so I'm taking bounds into it. I should have taken x1 here, but I, since I will be choosing x2 such that when I multiply x2 with that one, so basically I'm taking norms on both sides.
Okay.
I'm leaving this unattended for now because I don't know what the value of x2 is, and if I choose x2 to be such that which is already comes as a norm, then both sides I have x1, right? So if I multiply this here,
Mhm.
what happens? So I'm kind of finding bounds. So this becomes my x1, right, into whatever this is, plus when I multiply this, it becomes your minus of x1 into a phi x1 and minus of x1 beta 0. Oh, sorry, minus of, yeah. Yes. So this is the case. So because I chose my thing, so I took norm here because I knew that if the control that I'm choosing will bring x1 outside, so now everything has x1 in there. So I left one part. So I took a norm here, you're good, you're correct point, but I want to find an upper bound on this. And then I want to choose x2 such that this cancels this upper bound. That's why I kept absolute mode there, but not here, because I want to choose x2 such that the multiplication becomes so this and this cancels out, and then you're remaining with this minus beta 0 mode of x1. So this is a concept. Like now you have used sliding mode now instead of. So what is your x2 desired, or x2 desired, or your phi of x1 is basically your minus of a phi x1 plus beta 0 into sine of x1. That's it. So now that is my x2 desired. So basically the next step, you want to choose such that that this x2 goes to this value. Okay. So now, so basically this is x2 desired, this is not actual x2, right? You want your x2 to go to this value. Okay, so in this case, what will you do? You will do is, again, you can rewrite your eta dot equation, right? What is eta dot? Eta dot is your theta 1 phi of x1 plus what was that? x2, right? So x2, and then you can write x2 desired here, which is this, right? x2 desired plus x2 desired and minus x2 desired plus x2 desired, right? And then you can define that this term is z, right? And then eta dot can be written as eta dot theta 1 phi of x1 plus x2 desired plus z, right? And z dot can be, z dot will be tricky, like in real, like when you have real numbers you will find out, but z dot will be basically, z dot will be x2 dot, which is what? I think it is theta 2 psi of x1 x2 plus u minus x2 desired dot. Let's keep it that way, because x2 desired is this, taking a time differentiation, you will have to either write some dirty differentiation technique to compute x2 desired, because it might, because of the non-linearity, it might not be differentiable at x1 equals to 0, and so you will have to have to estimate this x2 dot desired rate. You can have an upper bound for it, so not a problem. But for now, let's just keep it that it is x2 dot desired, which or you can compute. when we do actual problems, we'll find out how that can be done. Okay, so that's your new problem. So now your v2 will be v1 plus half z squared, right? So backstepping, same step, and then v2 dot will be v1 dot, and so if you see your v1 dot, if you plug that, where is my v1 dot? Yeah, v1 dot will be, so v1 dot plus zz dot, and v1 dot I believe will be minus, so this is less than equal to minus beta 0 x1 plus so that's with this, and now with this it will be x1 into z, right? That's your v1 dot plus zz dot, so that will be z into z dot will be this quantity. This is theta 2 phi of x1 x2 plus u minus x2 dot desired. Okay, and now you can bring this in here, right? So it is less than equal to minus beta 0 x1 plus z x1 plus theta 2 phi of x1 plus x2 plus u minus x2 dot desired, right? So now we are at least at a stage where we want to choose u such that the whole thing becomes negative definite. But again, what are not known? This x2 dot desired is not known properly, right? As I said, you can have an upper bound on it, you can have an upper bound on this, right? So same like second step, but you see your u will be a combination of two sliding manifolds. That will be interesting to see. So if you see, I can, so if I say, okay, less than equal to minus beta 0 x1, so I can take so this quantity, right? The upper bound of on this quantity and this quantity, right? So you can combine all this stuff. So z into x1 minus x2 dot desired, and if it is known, you can directly cancel out. If it is not known, then you can say x2 dot desired, what is that, plus theta 2 psi of x1 x2. Okay, so this can be something, you can call it rho of x1 x2, right? Something like that, and you can use the upper bound concepts plus u, right? So again, rewriting it, minus beta 0 x1 plus z rho of x1 x2, right, plus u. Simple. So right. Simplify it at least, not if not simple. So let's say now, so now I can again do less than equal to minus beta 0 x1 mod of z, same approach as we do, mod of your what to say, modulus of this rho x1 x2, whatever that upper bound is. You can use, instead of theta 2, you can use b and all that stuff, right? So plus u into z, or zu. So what u should I choose now such that so you can see that u of sine of course z, so u equals to minus rho x1 x2 plus some rho 0 into sine of z. That will give me this v2 dot to be minus of x1 beta 0 and minus of rho 0 z. So that definitely is negative definite. That means both x1 will go to 0 and z will go to 0. Okay, but you see, if you go ahead and start plugging in things, because see where is that, so you will see that x2 dot desired, it's a function of something, which will be function of, because what was x2 desired, right? Oops. What happened? Okay. So if you see x2 desired was this, so which is again a function, you will, it's kind of complicated, but you get the idea, right? Wherever you don't exactly know the state which is your, that is the perfect, that's the ideal condition, right? If you exactly know what you're cancelling, then these upper bounds are not required. So what you do then, you are cancelling the maximum, you are applying the maximum cancellation multiplied by that sign of that quantity. So that combined with this gives you the adaptive. Implementing this, like, you should see like how interesting that you, when it goes to the MATLAB and actually makes it work, will be useful. Okay, so that's one case. So let's, I think there is a assignment 14.2 which I gave you. I told in the assignment that I will solve in the class. Is that something what I told?
Yeah.
Okay. So, and you guys can see, I can also show you the simulation for that. So that is the underwater vehicle problem that we are doing in the class.
Oh, really?
A simpler version of that.
Okay.
So.
No injuries. This is actually an open claim that's already going on.
So it's 14.2 problem, and so this is a UUV, unmanned. So when you are in water, right? So.
Unmanned underwater vehicle.
Yeah. 14.2, or you can call it AUV, right? Autonomous underwater vehicle. So that's more fun. Unmanned is less, is restricted, right? In water vehicle in which man can be there, but it is autonomous. More general term. So you have this AUV, right? So what happens there? For example, psi double dot for each equals to A. So you're, let's say, we're talking about one state of the UUV, which is the heading. Okay. So there are two terms. The heading of the UUV is proportional to the psi dot into psi dot equals to tau. So that's the simple equation. So this is a drag term. This is called quadratic drag. So why? So the idea of drag is that if you are having motion, right, the psi dot is what you're rotating around your this axis, right?
Mm-hmm.
Vehicle is. So when you are rotating, there is a drag. Okay. But generally, if drag is linear, then you can say, okay, it is opposite to the direction of velocity. But so let's say I rotate this side, right? So the drag is opposite side. So if your psi dot is in this direction, your drag is opposite to that. Okay. So this term, why this term came? Because, but it is proportional to the square of the turn rate. Right. So if I write a psi dot square, this should have okay, but this does not give me all that, whether it is negative or positive, it will always give me one sign, right? That's why this absolute value psi is introduced, that that direction comes in, because psi dot into psi dot is sine of psi dot into psi dot square, basically, right? Negative of psi, no, not negative, but yeah, sine of psi dot into psi dot square. So that's why this term implements this, so that to give me that opposite drag. If I don't put that, then drag is basically same, is always acting in one direction. Doesn't matter whether you're rotating this side or this side. So that's why this term has to be introduced. So when they did the experiment, they found out that drag is proportional to the square of velocity, right? But opposite in the direction of which it is acting. So that's why they came up with this psi dot into psi dot, which kind of captures that quantity, and A basically is the coefficient of drag. So that's how, and if you see all the equations in the underwater vehicle, they are quadratic like this. Okay, there's a one simple problem. So now you have to come up with a torque to give you a desired heading, right? Or track reference trajectory, basically. Psi desired time or whatever that is. Okay, and only thing given to you is that some this a. So it's given that a has a nominal value, which is a hat, which is a nominal value. So from nominal value, this thing is k, less than equal to k. Okay, and the psi reference, the trajectory that we have to track, psi reference of t is sine of 2t. So we want to track a trajectory which is sinusoidal. So your heading of the vehicle should be doing the sinusoidal motion. Okay, and so that's a very simple one-dimensional UUV problem, because each state of UUV will look like this: phi dot, theta dot, psi dot, u dot, v dot. Everything will have the same nature of equation. So we can design. So got it. So these are the parameters given to you. Your reference trajectory is this. This is this. So let's pose a problem. We can define our states first. We can say x is psi minus psi r, and that is x1, right, which is x1, and then x2 is psi dot minus psi r dot, that is your x2. So we can put our problem in a error states now, right, like we did in differential flatness and any problem that you, because goal is to take states to 0. So here is states going to 0 means we are on the reference trajectory, right? So that's the idea here. So these are our states. So let's say x1 dot equals to x2, right? And x2 dot equals to psi dot, which is what? Which is equal to, see, we have psi double dot equals to minus a psi dot into psi dot plus tau, right? Now we have to convert this equation because now we have reference. So if you see from here, x1 will be, if x1 equals to psi minus psi r, then psi r equals to, oh sorry, psi equals to x1 plus psi r, right? That's one. And similarly, your x2, your psi dot equals to, what is that? x2 plus psi r dot, right? So that's what you should replace here. So basically right, so it will be, so psi double dot basically will be equals to minus of a, and what is psi dot?
x2 plus,
so x2 plus psi r dot into modulus of x2 plus psi r dot plus tau, right? So your x2 dot will be psi double dot, which is this equation, right, minus a x2 plus psi r dot plus x2 plus psi r dot plus tau minus double derivative of this, right, psi r double dot. So that's our new equations of motion. So that is like half victory. If you are able to put things in this way, that's the half thing is done. Otherwise, so that's our new equations of motion. Now x1 going to 0 and x2 going to 0 means you're tracking the reference trajectory, and we have to find a tau to do that. What should be my tau such that this reference trajectory is tracked? Okay.
so that final minus
Hmm?
psi double dot.
Psi r double dot, right?
So how did that come?
See, if this is x2, what is x2 dot? x2 dot will be psi double dot minus psi r double dot, right? So, okay. So now we can start from here and do the math. So you can see now. So let's define. So what I can do is, let's choose a sliding manifold S, which is equal to x2 plus some a or alpha, I would say alpha of x1, right? Same thing, no problem. Like so which means if v1 equals to half x1 squared at sliding manifold, same you will see that what will you see? You will see that is x1 dot. So v1 dot is x1 dot, which is equal to x1, and x1 dot is what? X2, right? So and x2 is from here is minus of alpha x1, so minus alpha x1 squared, right, on the manifold. So if you are on the manifold, your x1 will go to 0. Okay, that's the case. So now let's come to the manifold now. So we want, so v2 is nothing but half s squared, because now you want s is not 0, right? That only is true when, this is only true when s equals to 0, right? So if s is not equals to 0, your u should push s to 0, so that is the reaching phase. So now v2 dot will be equals to s dot, right? And what is s dot? S dot is x2 dot plus alpha x1 dot, which is x2, right? So x2 dot plus alpha x2. And what is x2 dot? X2 dot is here, right here, right? So which is s into minus a x2 plus psi r dot into x2 plus psi r dot plus tau minus psi r double dot plus alpha x2, right? That's my quantity, right? So now there is a crux here. So if you see, there's a thing that we have to use. See, we don't know even the upper bound of a. We just know that from nominal value, the deviation from nominal value is k. So we have to interject there. So we will have to, what we have to do is convert this thing to the so that it becomes as a difference of now. So we can add, what we can do is, we can add and subtract a hat, same thing, x2 plus psi r dot. Nominal value is what is known to you. So you say that, hey, this is the nominal operating condition. I don't know what the deviation is, but most of the time it works there. So let's say this is known to you. So I'm just adding and subtracting this value here, right? Plus a, minus a hat x2 plus psi r dot right, plus actual thing minus a x2 plus psi r dot x2 plus psi r dot plus tau minus psi r double dot plus alpha x2, right? So this our expression is. And then if you see, what was that? A hat minus a, right? What was that? A hat minus a, right? So this and this, see, if you see this and this, so that will come out equals to a hat minus a, right, into x2 plus psi r dot into x2 plus psi r dot, right? So that's a minus this is this, and then minus a hat. Remember, a hat is known to you because it's a nominal value multiplied by x2 plus psi r, okay, plus tau plus tau minus psi r double dot plus alpha x2, alpha x2, this. So that's our s into this, that's the term. Okay, so see why did this, so this is known to me, good thing. So anything that is known to you can be cancelled. That's feedback linearization. So now I have to choose a tau, right? I have to choose a tau such that I get a v2 dot negative definite, right? That is the objective. So the problem is this is not known to me. I only know the upper bound. So now we can do that. So let's first cancel this out. So anything which is known to us, let's cancel it out to make it thing simple. So now if I choose my tau to cancel this out because this is known to me, let's make it blue. So this quantity is known to me. This psi r double dot is known to me because it's a reference trajectory, and alpha x2 is also known to you. So you can choose your, let's choose a tau equals to a hat x2 plus psi 2, psi reference dot plus x2 plus psi reference dot modulus plus psi r double dot, right? This will cancel this, and minus of alpha x2 plus mu, that additional mu to cancel the unknown terms for now, right? So when I plug this in, what happens? It becomes s into a hat minus a x. It's very important that we follow the bookkeeping method logically, otherwise you will be lost if you are doing this stuff. So into x2 plus psi r dot, everything cancels out, so it is plus mu. So see, now I can go and choose mu to make this clear, but that mu would be added here. So that's my tau equals to this, but now mu appears. Now I can choose mu to cancel out this. So now if you see, my v2 dot can be less than equal to mod of s, right? And the upper bound on this will be, what is that, k, right? The upper bound on this is given k, so k. And then if I take absolute value of this and this, it becomes basically x reference plus psi r reference dot x2, sorry, this is x2 plus psi r dot x2 squared, right? So basically taking mod means squared plus mod s into mu. Okay, so plus s into mu. So now I have to choose mu such that this becomes negative. So mu can be equals to minus of this quantity. So this is k plus x2 plus psi r dot squared plus some anything, some alpha 0, beta 0, whatever you want, into sine of s. Right? So this then will be v2 dot, if then will be minus of beta 0 mod of s. That's negative, right? So what is your control now? So this is my mu. So mu means my control will be, my control is this, right here. So my tau basically is equals to a hat x2 plus psi r dot into x2 plus psi r dot plus psi r dot minus alpha x2 plus, minus of k x2 plus psi r dot squared plus beta 0 into sine of s. What is sine of s? What is s actually? S I Jin. S is x1 plus
When it's 0, you're on the manifold, and
x2,
the
right?
sign of it drives you to it, right?
Hmm?
You ask what S is, like when S equals 0, you're actually on a manifold.
Yeah,
When it's not, it
yeah,
drives you to it.
yeah. So basically this controller pushes you
Yeah.
towards that quantity. Once you're on that quantity, you're good. Good. So that's I like this example because it's neat. It's neat in the sense everything, like it's like it makes sense, like you're tracking a reference trajectory like you have done for differential flatness, things like that. But the only thing is you don't know. And to remove chattering, you can use saturation functions and then do don't have to change anything. Analytically, you can say if you use saturation function, what will be the bound and all that stuff. Let's see if I have the code for this on MATLAB here. Right, so nothing like, I did not break any rules here, and that was the neat thing, and nothing was hard in the sense why I am choosing this or that, right? At least that was clear, right? Simple, no candidate functions, cancellations and everything. If something is known directly, you don't apply maximum cancellation. If something is known, you clearly cancel it first, rather than multiplying something into sign of as. That's bad. And what I'm saying is this.
So I
See,
just have a-
see, I could have cancelled one last point then. I could have cancelled. I could have lumped this all together and said there's an upper bound on this, and then that's not good, because then anything multiplied by that sign of s will be bigger.
So like in the future with a bunch of experience, like can we see, can you scroll up just because I want to see. So like one question you just asked of, like conceptually, like what is that sign of S doing? And you say it's driving you towards the manifold. So can each of these terms, well, like with your experience, eventually you can look at that and know what each part of that controller is doing?
Yeah, so that's
Like without going through the math, it's just like, hey, this part kind of does this and this part kind of does that. Like, is that a feeling
Yeah.
you'll be able to develop
yeah. So
later on?
this is for feedback linearization.
Okay.
So and then you already know that x2 psi r, like everything, like x2 is going to, this all quantity, like x2 is going to 0, right? X2 is going to 0, and then so this all should disappear at the end.
It's like, eventually I have to know how to check all this stuff.
So
right?
yeah, I
After
understand
years
what you're
and
saying.
you're
Well,
just
how
like,
does
this
this
pass the look right test? Like, 'cause to me this means nothing. Like, I see you go through the math, but will we develop, not after this class, but like, in our profession, to look at this and know exactly what it's doing? Like, is that a gut feeling that you eventually develop?
Yes, I think you will develop
Okay.
that gut feeling, but that is not that intuitive that you can look at
Okay.
this expression and that tell. You can not do that in linear system also, right? U equals to minus kx is the controller for linear system,
Mhm.
right? All the linear system, right? How could you just look at it and tell it is doing what it is supposed to? Until unless you go and tell what if my a minus bk
Okay.
has negative eigenvalues, then only you can tell, right, if this controller is working. Similarly, I know that if this controller is plugged in, it is giving me v2 dot is negative definite, then only I am able to say. So
Okay.
say that negative definite is equivalent of saying eigenvalues are negative here, right? So it's, yeah, you intuitively,
I mean, it's hard, is what it
yeah,
sounds like.
it seems
okay.
like it's not that, like, even like, so my question to you will be this then. How do you know in a PID controller, let's say I have a PID controller, right? So what is a PID controller? U equals to Kp into error plus Kd into minus Kd into error dot plus error dot plus Ki into that integral. How do I know that for what values of Kp, Kdi is this system going to be stable? You go and plug it in and see if my eigenvalues are negative or not, right? So this is similar. You go and plug in your V2 expression, V2 dot, and you don't have to check it, right? Because you derived it in that way. So this came out from that perspective. They're different. The linear system, it was different. That okay, I've chosen this Kp and Kd. On this when I use this Kp and Kd, will my eigenvalues be negative? You don't know. Because that if you are using LQR, that was kind of understood. Like there is an internal theorem which is, if you use that, your eigenvalues will always be negative. But same thing here. So yeah, the only bad part here is that it looks ugly. Then this looks simple, right?
Okay.
But just remember, if A is a 4x4 matrix or 6x6 matrix, and finding A minus BK eigenvalues, you tell me if that will be easier or not. But okay, here you are dealing with a scalar function which is V dot. So the only thing is it does not look that nice. Okay, so let's see if I have the simulation. Let me check if we can simulate this. Yeah, we have it. So UUV sliding mode problem. So that's yeah, I'm amazed. Like first time when you implement this and say, hey, this works. It's a good feeling to have. So for you don't want to record this, right?
Oh, okay.
So if I run this, there's my MATLAB. So parameters are there, right? So if I have initial states psi and psi dot, p dot a. See, p dot a is only used for simulation, but for controller I don't know it. See, your simulating model you need to know, but the controller, the person who's controlling, does not know. So my controller does not have knowledge of a actual a. It only knows that this thing, that a minus a nominal is that. Okay, so a nominal is known to you, that let's say a nominal is 1, and that the difference is, we can change these values and see how things look like. But, so my UUV dot m is this. Same 2 states, 2 outputs, 1 input. And it's very simple. It's same x1, x2, and then x2 minus a, x2 absolute value of x2 plus u. It's a very simple equation from that. You cannot, such a simple system, the u is like even 10 times bigger than the actual state space. Is kind of, but that's how life is, right? So now let's show you the control file. Where's my controller? So the controller is same. Again, I need, so you need x2, which is, you can define what your x2 is. I think this is where the awesome controller will come. Is it, I think this is for students. This
Yeah.
file is for students, but anyways, so I should have, it's somewhere, not here. So yeah, if you see, this is my x1 is defined here, right? X1 is psi minus psi reference. So your S function is giving you psi 1 and psi and psi.
Oh, okay, God, I was confused by that, okay, okay.
But you have to convert it to x1 and x2. So you convert it, and then basically your sliding manifold is alpha x1 x2. All those terms are defined, and basically you have to type. What do you say? We type it in, or we
Sure.
go and copy things?
You already got it, calculated.
So let's type it. Or maybe let's see if I have it, then why should I waste time, right? So somewhere, OneDrive, imported from box. Somewhere, if you see nonlinear controls, let me know. MATLAB, adaptive, UU sliding mode.
1.2, there was a photo right below it.
Huh?
Right below where you just clicked, 14.2.
Yeah, so I think this should be the one which 14.2 should be for the students, I believe. Yeah, this is there. Right. So run this, change folder, and then let's see. Okay, so if my controller is there, no problem. And I can so what we are doing in the controller is, for example, if you see, even if you see our notes, right? How do I? So if you see my notes here, right? So I had, what was my tau? If you don't plug things in tau, so I always say students always go modular. So this is tau, right? Tau equals to this all feedback linearization plus mu.
Right.
Rather than writing this whole term in
Yeah.
one thing, that you can get errors, because
Right.
then you can find out what my mu should be and this should be. It's easier to debug. So that's what exactly I've done. My mu is minus k x2 plus psi dot psi r squared plus beta 0 into some saturation function, or you can use sine function. Initially we can use sine function here. Saturation is to avoid the chattering parts, mu, and then basically you can add your tau equals to whole this shebang plus mu,
Yep.
right? And that's the end of it, right? So let's go. So control S, and then controller is there, and then I think we are getting this dot psi reference, and double dot psi reference in as in differential flatness from a target file.
Okay.
So the target is giving me psi reference dot, and psi reference double dot, which is used here. See, to compute x1, we need psi and psi reference. We need so psi and psi dot is coming from S function, but psi reference dot, psi reference double dot is coming from the target file. So the target file is very simple. It's just simple sine 2t, 2 cos t, and minus 4 sine 2t. It's this psi reference dot, psi reference double dot. Okay. So that's not a big deal, right? So now let's open our awesome simulation. Anyhow, like what amazes me always is this all complicated expression and everything. When it works, it gives me a good feeling. So this is why I like this class, that because the concepts are just more like V and V dot only, but we go into things, like we take steps and go in and show things. Like in other classes, like even like from undergrad's perspective, the UAV class, there are some things where we just hand wave, right? Like how wind model, hey, wave we want, okay, you magically got the wind parameters, which you cannot go and investigate how they got the Diedron's wind model or something. So is it open yet? Okay. So if you see, this is my, so you have a UUV, which is the S function. You have a target file, which takes time in and then gives psi r dot, psi r double dot. This goes in, and then I don't think I have any simulation as such animation, but I will show you the plots once we run it. Okay, so now let's go and plot data. So in plot data, I have all the states, right? So let's see. Okay, let's see. With figure 1 should be figure 4, figure 3, figure 2, and figure 1. So the red one is the psi reference, right? Psi reference. So that is how it is time changing. And you see, it takes quite a bit of time to catch. Like even in 50 seconds, it has not catched, but you'll see it's getting closer, right? It's getting closer. Similarly, you see psi dot, which is the X, right? And then figure 3 should be what? Control or what is that? U. So that's my control, actually, right? And then figure 5 is my x1, x2. That is my plot. So you see that this is a reaching phase. And then once you reach here, you're going towards the origin. So when it goes to the origin, that's when those two trajectories will superimpose, if you see. But let's see if I can increase some simulation time to, so, and we can change some parameters like K's and things like to speed things up. So So now if you see in the figure 1, so it started here, right? That's where we are starting. Slowly, slowly, slowly. And after that, you see it's caught up. So after that, it took some time, quite a significant amount of time, actually, because the sliding. I think the question is either what A is. Once it reaches the manifold, right? Of course, there is chattering terms there, but after that, this manifold thing is taking too much time. I think. See, it started here, and then it is. That's where it reaches, right? 0, 0. So 0 here, and 0 here, right? So remember, these are x1, x2. That means psi minus psi reference, and psi dot psi minus dot psi reference. So let's see. So that's kind of the slope. What is the slope that I'm using? Do you know? Target controller. Param dot m. So p dot alpha is 0.2. What if I make it 1? Hold on and see. So that slope should be 45 degrees now, right? We should make it 70 seconds should be okay. Very slow. But it caught up. So good thing is we didn't know the nominal value thingy. We can change that also.
It almost didn't even appear that U itself looked efficient. It just looked like a sine wave, and it didn't look like. I don't know. It just seemed like it.
Yeah,
did the
it's
exact
because
same
see
thing the whole
the
time.
the sine function is plus that additional cancellation term is also there, right? So you're constantly cancelling that term, which is
Like the magnitude of it didn't
Yeah.
change or anything. It looked like it did the exact same thing the whole time.
let's see. That's a good. So figure 5, I don't know what that is. So this time it went pretty quickly to see I think the manifold from
Okay,
here
so it
was
overshot it?
40, yeah, it kind
Okay.
of overshot it, but
Hmm.
if you see, that's U. So U initially is big, right? Once you are on manifold, the only term that is you are seeing is that cancellation term. If you see your function, if you see your controller right here, this controller is a part of mu, which is the S part. Mu is the part which depends on this sliding manifold, which is 0. When you are manifold, this term is not there. But you are
Okay.
constantly cancelling out
Okay.
terms because of this part,
Okay.
which causes that. So initially, see, the job of this guy, mu, is to force for the reaching phase.
Okay.
Once it reaches, the only thing that remaining is that cancellation. So that will be there. So this will. So this is my U, but you see, in this case, figure 1. If I see figure 1, it is somewhere. Figure 1. This time, see, pretty
It
quickly.
got quick, yeah.
So that slope matters. The manifold slope matters. So you can also use saturation function also to see what it does, but we can use that. Let's see. Saturation function right now may not be that important because there is no noise and all, but if I put some noise into it, then it will be. Very interesting. So
Be
that's the
interesting to
beauty of
implement.
like you didn't know the parameter, but you were able to catch it.
Still control it.
That's beauty here. And slide it down. So what happened this time also? So this time, I don't know if you call it smoother or not, but it definitely caught up initially only, same thing, right?
Yeah.
And No, this is not the control, right? Exactly. Same thing, and then it does. Remember, I was telling you that when you use saturation function, it does not exactly go onto the origin, but in a neighborhood of that. So if you zoom this part, yeah, you'll see that you can actually numerically found what this bound. So you get that close to the origin. See, so this is origin here, right? So this is the bound. How close you get to the origin. So it is this side 0.015 and this side 0.10 to the power minus. So pretty close, pretty close to the origin, and but that's good. You remove chattering, but you're still able to go to. And the chattering will be more prominent if you have noise in your states. If you just put some noise, you'll see there is more chattering, and the saturation function there will be. So for real-time implementation, saturation function will be must. Otherwise, you will have lots of chattering because of noise. So yeah, this is like problem 14.2. You would have done it, but still you have to do it. I'm not giving you the code or anything. You just very simple 2-line codes of S function, 2 lines of controller. So I'm not giving you anything. You just recreate it. Okay. I think earlier I might have given files to people. You guys have done enough of S functions. Okay, so that's the idea here.
Or maybe we'll just write our own MATLAB function and add an integrator.